Hi, welcome to video 9.5, C, Absolute and Conditional Convergence. Okay, again, a reminder from this point forward, all the tests will be there. Okay, so we have nth term, geometric, integral test, p-series, and harmonic, direct comparison, limit comparison, alternating series. The only one that I won't be throwing in from this point forward is sequence of partial sums. Okay, so page 636, they start talking about absolute and conditional convergence. So, absolute convergence. If the series summation absolute value of AN converges, then the series AN also converges. So, therefore, if you have, for example, a alternating series, you could say, oh, if I take the absolute value of it, which means I get rid of the -1 part, then I could just check that. If that converges, then my original series converges. Okay, however, the converse is not true, i.e., if the summation of UN is convergent, that then does not necessarily mean the summation of the absolute value of UN is convergent. Okay, so it only works in this one direction. If the absolute value series converges, then the original series converges, not the other way around. Okay, now definition of absolute value and absolute and conditional convergence. So, if AN is absolutely convergent, so that's where the word absolutely comes from. Summation AN is absolutely convergent if the summation of the absolute value of AN converges. Summation AN is conditionally convergent if summation AN converges, so it is a convergent series, but summation of the absolute value of AN diverges. So in each case, the summation AN converges. The question is, does it converge absolutely or does it converge conditionally? And that means that you've got to check to see whether the summation of the absolute value of AN either converges or diverges. If it converges, then summation AN is absolutely convergent. If it diverges, then it's conditionally convergent. Okay, in exercises 51 through 70, so let's have a look at that. Okay, it says determine whether the series converges conditionally or absolutely or diverges. So there's three possible answers. One is the series diverges, the other is that the series converges absolutely, and the third option is the series converges conditionally. So, but it's one of the three. Okay, so there's two different ways you can approach this, and you'll never know which one's going to be shorter. First procedure is to check the summation they gave you, the summation AN, because if it's divergent, you're done. You're done. If it's convergent, then you're going to have to go through the process of deciding whether it's absolutely or conditionally convergent. So you're going to look at the summation absolute value of AN. You're going to look to see if that's convergent. If it is, then your original series AN is absolutely convergent. If that series of the absolute value is divergent, then your original series AN is conditionally convergent. Because remember, we did establish it was convergent. On the other hand, you can start, instead of starting with the series they give you, you can start with the series of the absolute value of what they give you. If it turns out that that series is convergent, then your original series is absolutely convergent. If it turns out that it's divergent, unfortunately, there's no conclusion for your AN. If, on the other hand, okay, so there's no conclusion right now, but if it's divergent, you would still have to go back then and check to see if AN is convergent or divergent to see whether it is conditionally convergent or simply diverges. So personally, I think I would go with this one, and I think it's more straightforward. Check the original series they give you. If it's divergent, you're done. If it's convergent, then just check the summation of the absolute value of what they gave you. If that's also convergent, then your original one's absolutely convergent. If it's divergent, then your original series is conditionally. So here's number 56, obviously a alternating series. This series is an alternating series where the an, remember the whole thing here is the un, but if we take away the negative 1 to the power part, we're left with 1 over n plus 3. So this is positive, this is decreasing, so it is an alternating series test, and we find the limit as n goes to infinity of an, which in our case is 0. So the series converges by the alternating series test. So now the question is it absolutely convergent or conditionally convergent? So what you're going to do is you're going to take the absolute value of the original series, okay, of the original an. That's going to make the negative 1 disappear. And now I'm going to use a limit comparison test on this one, okay? The nth term test fails. It's not geometric, etc., etc. So my ANs are positive, and sure enough, you can then do the limit comparison test. I'm going to get rid of the 3 and compare it to 1 over n, which is the harmonic series, which is divergent. I'm going to find the limit as n goes to infinity of my given un, 1 over n plus 3 over the vn, the thing I compared it to. Simplify that. You find out that this limit is 1. Since that's a positive constant, that means that if the original series, that if the one we compared it to diverged, then ours is also divergent. And if it had been convergent, the one we compared it to, ours would be convergent. But it was divergent. So this particular series diverges. I shouldn't say also diverges. Oh, yes, I can say also diverges because this was the divergent harmonic series we compared it to. So because the summation of the absolute value of an is divergent, then the original function, which we had found out to be convergent up here, right? We had found that it was convergent, but we found out that it is what is called conditionally convergent. Okay, number 58. So that's your UN. I'm going to go with Plan B just to show you Plan B. So let's start with the absolute value of it. So the negative 1's gone. Of course, that simplifies down to a P series. P is 3/2. Since P is bigger than 1, the series converges. So since the series of the absolute value of n is convergent, then the series of just UN is absolutely convergent by that theorem that we saw. So again, our wonderful review of all the things we could have. We could have nth term test. That works with any series. If the limit as n goes to infinity of un is not 0, then the summation un is divergent. If that limit is 0, there's no conclusion. You got to try another test. If it is a geometric series and the absolute value of the common ratio is less than 1, the series will converge to the first term over 1 minus r. Remember to write out the first few terms to be sure you have the correct first term. If, on the other hand, the absolute value of the common ratio is greater than or equal to 1, the geometric series diverges. P series, well, the special case harmonic series, summation 1 over n, that's divergent. What does that say? Oh, if it's non-harmonic, which means P is really not 1, but whatever, 1 over n to the P, then if P is bigger than 1, the series converges. If P is less than or equal to 1, the series diverges. Remember that you can pull a constant on the outside of a summation. Remember, convergent plus or minus convergent is convergent. Convergent plus or minus divergent is divergent. Divergent plus or minus divergent is no conclusion. And in which case you'd have to combine the terms. Direct comparison test, your UNs have to be positive. If the summation Vn is convergent and Un is less than or equal to Vn, then summation Un is convergent. If summation Vn is divergent and Un is greater than or equal to Vn, then summation Un is divergent. Limit comparison test, again, the terms have to be positive. If the limit as n goes to infinity of Un over Vn is a positive constant, then both series converge or diverge. If it's 0 and the series you were comparing it to was convergent, then your original series is convergent. If not, no conclusion. If it's divergent, if it gives infinity or negative infinity, and you were comparing it to a divergent Vn, there should be a Vn there, and summation Vn is divergent. So let me stick that in there. It would be nice if I could do this. Okay, so summation Vn So if summation V, oh my, oh that so doesn't look like a V. Let me pause. Okay, so if that limit was equal to infinity or negative infinity, and your original and the series you were comparing it to diverged, then your series diverges. Alternating series, make sure it is an alternating series. The AN, which is the part not the negative 1 to the power part, but the rest of it, if that's positive and decreasing, and if the limit is n goes to infinity of AN is 0, then the alternating series converges. Now, your book's going to say otherwise there's no conclusion. Well, there's no conclusion from the alternating series test, but if that limit doesn't equal 0, you are right back to your nth term test for divergence.